Hi, hello, good morning, everyone. Today I wanted to talk about supervised learning, and I'm gonna basically follow and comment some online tutorials that I think are very, very well developed. So these online tutorials are machine learning with Torch 7. They were developed by Clement Farabet at NYU, and they're used by Jan LeCun and several other people in the field. Torch 7 again is becoming a very popular package in the use of machine learning and in particular deep network. So I wanted to tell you a little bit about this tutorial. In particular, I will start with the supervised learning tutorial, and I'm just gonna try to comment it slowly. So we'll start with number one. Step number one is look at data. So this tutorial have 5 files: data, model, loss function, training, and testing, and we will go through quickly each one of them just to take a look at it. So in this tutorial, basically we'll be using the street view house number dataset, which is a real-world image dataset for machine learning and object recognition. And it's small and it has a minimal requirement data preprocessing formatting. It's basically the new version of MNIST. The MNIST was the one cropped digit from that Jan LeCun spent a lot of time working on, starting up convolutional neural network on basically reading checks from banks. It basically has a lot of cropped digits, but it has also a huge amount of labeled data, more than 600 digit image, 600,000. And it comes from like a significant hardware unsolved real world problem, which is recognizing digits and numbers in natural scene. So this Street View sound number is obtained from house numbers in Google Street View images when Google wanted to, for example, clear out all the tags of the cars that have been seen on the street, just to not to violate privacy. So this data set has with 10 classes, one for each digit. So digit 1 is labeled 1 and so forth. There are 73,000 digits for training and 26 for testing. And there are additional 331,000 additional, maybe a little bit less difficult samples that they can be used also as a training data or so forth. So it's MNIST-like. So the original image are character with a bounding box. In this case we use a 32 by 32 image centered around a single character. Many of the image also contain distractor on the side. So the input images are basically 32 by 32 and the output is 10 dimension. So in the script that we have written by Clement Farabet, you load the data from the disk, and then you rearrange it to be compatible from Torch, basically. The data in X is basically 4 dimensions. The first dimension indexes the sample. The second dimension indexes the color, and the last 2 indexes the height and width of the sample, so of the image pixel. So preprocessing requires a floating point representation. The original data was really basically stored in bytes. Nowadays the images were stored in bytes. So you can really convert pretty quickly the entire, once you load the entire data set. Look at the data set, how it's done. Basically there's the train data is a data, is a label, and then there's a function size which return the size, how much data you really have. So all you have to do is train data.data, you cast it with this command of float. You can have double, byte, int, and you convert the whole thing into a single usable data set. Now we're going to explain a little bit about the preprocessing of the data. Preprocessing is used in machine learning pretty much everywhere, and there are several tricks for natural images. First of all, images are mapped into YUV space. They separate luminance, so the black and white information from color information. This is not really a biosphere approach, as in the human eye and some of mammalian system. Somehow we maintain some kind of a RGB, we basically maintain some kind of an RGB representation. So personally, even though going to YUV gives you slightly better results, in my laboratory we tend to try not to use it as much, just because of the lack of biological inspiration, and also the fact that it's an extra step that gives you some mild advantage in some small networks, but it's debatable whether they give it to you in larger network. Anyway, the group from Jan LeCun showed that this is an important step, so in this case it's done. Then you want to locally normalize the luminance channel, so use a contrastive normalization operation. So you basically try to eliminate the mean, so subtract the mean and try to have a standard deviation of each sample equal to 1. So if you could do that in every part of the image, then you would basically boost the signal that is important, the content of the signal, but try to eliminate the rest. There are other techniques like ZCA whitening that are very popularly used, particularly by a group by Andrew Wang and other people. So ZCA whitening, Andrew group, others, is used quite a bit. This technique is used quite a bit. It's very costly though, and we don't recommend really using it. It also can be only used if you really have the entire data set to begin with. You also might want to normalize color channels globally, so that each color component has a zero mean and one norm across the entire data set. So these are basically tricks that act like a retinal preprocessing and try to squeeze the information to be compatible with what we see. So in order to do this in Torch, the idea is you convert all the image to YUV by going through all the trained data, converting each one of them to YUV with the image, RGB to YUV commands fairly quickly. We can name different channels with different variables very easily, and then we can normalize each channel globally, so you just get the entire trained data, the whole thing, you get the mean and you get the standard deviation, and you subtract and divide, so for each one of these channels. So you can do that, you normalize each one. And you can also normalize the tested data exactly the same way. In this case now we preprocess with local contrast normalization, so special contrasting normalization. It uses a Gaussian kernel as a neighborhood. So we set it up, is an NN function that you can call, number of inputs and basically the kernel used to normalize. And then what you do is you normalize each channel by sending them through normalization. So you can do normalization forward or normalization of trained data.data, and you save the same data right there. At this point you have the normalized. What is good to do is to try to Just go through and look at all the data, mean and standard deviation at this point, and then print for each channel mean and standard deviation of the training, test, and test data, just to see that everything is okay. You can also visualize with image displays a few samples, so train data.data. You can grab a few like this. It's similarly to what you do with MATLAB, so you can grab you know, the first channel, you can grab the first 256 samples, and then you can image them like this: Y channel, X channel, and so forth. This is all there is to say for the pre-processing step number 1.